Okay. Yes, so we introduced the Stokes parameters, and we saw that equation 43 holds for a strictly monochromatic wave. So we have equality between the total intensity, Stokes I, and Stokes parameters, and the addition of the Stokes parameters for the linear polarization Q and U plus circular polarization V. Now, last time we introduced this idea of a quasi-monochromatic wave. So the waves are signals which depend on time and position. This is a signal, and the spectrum, of course, needs to be calculated or extracted over the whole history, past and future of the signal. And of course, that's not possible. So in practice, we restrict the domain of the signal to some time interval. Okay, so it's like so the signal is supposed to be 0 until some time t, and then it's non-zero until for a period of time t plus delta t. And so this leads us to the idea that our signal, I mean, an electromagnetic signal here represented with the electric field, then can be decomposed into a sum of monochromatic or quasi-monochromatic waves like this one. So here we have this monochromatic, the usual monochromatic component, so one single spectral component, but the amplitude of it is also depending on time. Okay, so that the spectrum, which would be this vectorial factor here, is constant if we could integrate over the whole of time, but it's not the case. So if we want to restrict to a quasi-monochromatic wave, we have this time dependence in the factor here. Okay, so and I'd like to know whether there are any questions at this stage. So bear in mind that this is a representation of a quasi-monochromatic wave, which is not just a monochromatic wave, which would be this exponential form here, but it's also got time dependence into the factor, because that's why it's quasi. It's not quite a monochromatic plane wave. Okay. We introduced this last time, and now I'd like to go on finding this interesting relationship between the Stokes parameters for the quasi-monochromatic waves. So for measuring the Stokes parameters, I remind you, let's go back a little bit. Let me move this over here, perhaps, and then yes, so right. So you see that with the Stokes parameters, we had this, in order to calculate the Stokes parameters, we needed to compute products of this type. Okay, so go back further. Okay, so this is the plane wave. Okay, this would be a strictly monochromatic wave because E1 and E2 do not depend on time. And then these are the components of the electric field along the vectorial basis E1 and E2. Okay, so now going back to this the case of quasi-monochromatic waves, then when we want to measure the Stokes parameters, and you've seen that it's in practical terms we take averages of the Stokes parameters, so we need to compute this type of averages. These are time averages of the products of each component of the electric field. We plug this in, and we can compute the time average Stokes parameters for Q, U, and V. So this is a little bit tedious. I think it's done in the textbook. Well, let me go back again for the definition of Q. Here it is. So we inject Q equals this thing, then U equals this thing, and V equals that thing. Okay, so you just plug it in. Okay, and compute Q squared, U squared, V squared. You plug in Q squared, U squared, V squared, and you take the time average of it. And you'll find that the time averages then, well, the oscillating exponential goes away in all those E1 times E2 conjugates. That's where you kill it, the E exponential I omega t. And then after a bit of algebra, you can come up with this relationship. So you plug it in and you reach this interesting result that the sum of Q and U and V squared give you the Stokes I squared on average, corrected for this term, okay? Now, you can also rewrite this in this other way, where you replace this Eulerian notation with cos phi plus I sine phi, usual complex notation, and you reach this other form, okay? So maybe, I think this is done in the textbook, I'm pretty sure. But if this is puzzling to you, I recommend to develop this on your own. I mean, I haven't placed a tarea here, but maybe I should, because I think it's important to work this out. Now, notice something interesting here. The modulus of each component of the electric field, let's call this epsilon 1, epsilon 2, are statistically independent. Okay, so we have this. So we have that the product of epsilon 1 squared, epsilon 2 squared, because these are statistically independent, statistical independence, okay? And the same for the modulus and the phase. So we have epsilon 1 squared, epsilon 2 squared, times cos phi squared. I might have a typo, just realized. Yeah, the second term is probably a sine, not a cos. I'll cross check this, but it's probably a sine, not a cos. And wait, hold on a second. I need to check this. Let's bring up the textbook to see if I got it right or not. Unfortunately, the textbook does not develop this. It's probably taken from Jackson then. It might take me a bit more time to find out what's the right term. Okay. Let me go back to this. Right. So, and then my summary. So this is probably a typo because I've got twice the same thing. Okay, I'm assuming that this is a sine. I'll try to correct this later on. when I find the right expression. And so the idea here is this, is that cos phi squared by 2 minus phi 1 is greater, no, sorry, this is less or equal than so I don't know if you are following me here, because the idea is that this term, cos phi 2 minus phi 1, messes things up in terms of statistical independence, because of course this part depends on the component 2 and this part on component 1. So this is no longer statistically independent. And in this case, I can still write this inequality, because this number is always between 0 and 1, right? Because you know, cosine goes from -1 to 1, and so squared is from 0 to 1. And so we can guess that this average is going to be less than the average of just the modulus squared. Okay. So now, if you bear this in mind and look at equation 47 again, so imagining that you have a sign here, then you can guess that this corrective term, the big term here, is less than so it's less than this one. Okay, so let me write it down. I think it's better to write it down and not trying to explain this all with words. So what I'm trying to say is that yes, so epsilon 1 squared, epsilon 2 squared times cos squared. Yes, that plus epsilon 1 squared, epsilon 2 squared times sine squared of phi 2 minus phi 1. Okay, so all this is less or equal to epsilon 1 squared times epsilon 2 squared. So this quantity here is positive definite, is what I mean to say. So all this factor here is positive definite because of this inequality. Okay. So in other words, what's on the right-hand side of equation 47 is I squared minus something positive. Okay. This means that this whole thing is less than just I squared. So what I'm trying to say is this, is that I squared minus something positive is less or equal to I squared. So we have this inequality less or equals to I squared. So this is a very important inequality in astronomy. In the end, we see that while the equality holds for a really monochromatic signal, which doesn't exist in nature really, for a real signal, we have this inequality. Even for a quasi-monochromatic signal, as long as we have a stochastic dependence on the in the spectrum, as long as the time dependence, there is time dependence in the spectrum, then we have this inequality, and it can go down to the equality only for the case of a strictly monochromatic signal. Okay, so if we have, this is what I meant, you know, if we have a signal constant elliptical polarization, then we have the equality. And for a completely unpolarized signal, we saw from the experiments that the way we designed the Stokes parameters, that Q measured the degree of linear polarization along one axis. U was measuring the degree of linear polarization along the orthogonal axis. And V was measuring the degree of circular polarization. And so it can be that all Q, U, and V are 0 for a completely unpolarized wave. So if we go back here, for a completely unpolarized signal, we have no polarization in Q, nor in U, nor in V, but we can still have a radiation flux, Stokes I, because it's just unpolarized. So that is not quite easy to digest, and maybe I did not achieve a very clear description. So please tell me if there are any questions at this stage.
Professor?
Yep.
I have a question. What does unpolarized mean? Does it mean that the wave is polarized in any direction? In every direction? Or because I thought that, I mean, I can see linear polarization and circular polarization, but how is it not polarized at all?
Yes, Felipe, that is quite difficult to understand, because we showed that the electromagnetic waves are vectorial waves that always have a polarization. Each component has a polarization. So how come that the superposition of all those components can be unpolarized? Okay, so the way I think of it is like this. Well, let's think in concrete terms. I mean, this is not just about astronomy, of course. This is applicable to any electromagnetic radiation. Even in daily experience, But let's think of the astronomical context. Okay, so we have the photosphere of a star, and here we have some excitation process, that leads to a photon, with some energy at that frequency. Okay, and this is going to have a very specific polarization state, E and B. And then we are observing this far away, and we're not just observing that particular quantum of light, but all this superposition, of billions and billions and billions of billions of such events, And all of these have not necessarily the same polarization states, Others can be that way, others can go the other way. But here we measure the sum of all of them, So in the plane of observations, if this is the direction of propagation, and we look at this way, so the signal is coming from this direction, we have this electric field. And this electric field is moving all over the place because it is the superposition of all those signals, of all those pulses. Okay, so just to make things, something a little bit more concrete than this, imagine that we have a collision between an electron and a proton. And this is what is triggering the signal, okay? So this collision accelerates the charges and hence will emit radiation, as we'll see shortly. The spectrum of this pulse will be the superposition of such quanta, which are monochromatic components. Okay, follow me, yes? So, but these encounters can occur on very different angles and not necessarily in the same directions. And you can observe them in different directions relative to the plane of collision. So when we observe the photosphere of the star far away, we have a signal which is a superposition of all these microscopic events, And this electric field is moving all over the place. It's not rotating in one direction or the other. It's just, imagine it's like, it's moving, how can I, like maybe with my pen here, look at the camera. It's just jittering all over, like moving like crazy in all directions, you know? It's not, there's no simple time dependence of this electric field, okay? So what we see in the end does not seem to have any polarization. If, for instance, a case of a linear polarization would be when the signal for the electric field is always moving in this plane. Circular polarization would be always moving in circles, you know? And that could be true for any one of these components. But for the superposition of all of them, the result is stochastic. Sometimes this piece of star emits a photon, and then it doesn't anymore. Or sometimes another piece would emit another photon, and then it doesn't anymore. You know, whether or not a particular blob in the star will emit a quantum is a random event. It's stochastic. And the properties of this signal emitted by this blob are also going to be random. Okay, they all have the same frequency because we're looking at that frequency. We're considering this particular frequency, but the polarization of it is stochastic. Okay, so just to make things so super clear, if we are looking just at one collision event like this, okay, then we have a specific pulse. Then this is going to lead to, say, let's call it that's not a good notation. So this is going to radiate. Well, I'm getting a bit ahead of the contents of the course at the moment, but this collision will radiate electric dipole radiation, and when you look at it far away, like if we observe far away this collision, then here we'll be measuring an electric field, which will have a very specific time dependence. In fact, it's going to be linearly polarized. Okay, this collision is going to be linearly polarized. And so it will be a pulse. We'll see a sinusoidal pulse, linearly polarized, that will increase in amplitude as the electron and proton collide towards each other, and then decrease in amplitude as they recede from each other. But this is a pulse, you know, they come together, emit radiation, then go away again, you know. So another example, suppose that we have, this is not, well, it could be the photosphere of a cool star, one with atoms in it, you know, or maybe imagine a nebula or the Orion Nebula, where we have atomic atoms, you know, atoms, right? So we have, imagine that we have like, a slab, a uniform slab of a piece of interstellar gas. Okay, and in here we have atomic hydrogen. Okay, and so we have one decay. Okay, so typically this is the difference between well, it can be 2, 3, 4, 5, you know, just some transition for atomic hydrogen, you know, and so there are atoms in here that shine, okay, and they can decay spontaneously with the Einstein coefficients. I think we saw them, and so that particular atom has got this rate of probability of decaying. It might decay or it might not, but this is the probability that will make it decay. So if it does decay, then we have, you know, if we zoom in on this, then we have, you know, like this is N2, and then we have another inside closer level N1, and we have the electron jumping from one orbit to the other, and this emits some quantum of light. But this again is a pulse. Before it decays, it is an excited state, and then it lands into a lower excitation state. There's no radiation, it decays, there is a radiation, and then there's no anymore. This again is a pulse, okay? And that particular atom might choose to decay at some point. That one might choose to decay at another point, etc. Okay, so this is again a random process. And what you see far away is a superposition of all those individual pulses. Okay. So this connects with what I want to show you now about the sum of n different waves. Look at equation 49 here. So the total electric field is a superposition of all these individual pulses, you know. We can write this in vectorial terms this way. Now, each one of these spectral components, E1 and E2, are time dependent, okay? But they are statistically independent. Whatever happens to this atom is completely independent on what's going to happen to this other atom here a few AUs or even parsecs away. You know, like if the linear dimension of the atom is, well, you know, angstroms, and they are separated by astronomical units or even more. So when this one chooses to decay is completely independent on when the other one is going to choose to decay. There are some exceptions to this. For instance, when we have Maser amplification, okay, or laser amplification. But in general, they are completely statistically independent. And so when we take averages, when we average some component of some vectorial component of this first pulse K times this other pulse L, when we do this type of averages to calculate the Stokes parameters, we are led to Kronecker deltas because they are statistically independent. I mean, if I'm trying to say is this, is like in this, exactly in this example we're looking at, you know, when I take some component times another component, and let's focus on the X component, okay, for instance. When usually we take the compass conjugate, you know, if K is not L, if we're looking at two different places in the nebula, then these two are statistically independent, and so we factorize. And since these are algebraic quantities, they can be either positive or negative. Each one of them is 0. And so the average of these products gives me the Kronecker delta, okay? So once you calculate I, for instance, if you calculate I for this superposition here, all the cross terms are going to be 0 because they're statistically independent. And so I is just a sum of the Stokes parameter of each individual components. What we're saying is this: it's kind of obvious for I, but might not be so obvious for the other components. Sorry, K equals 1 to N. So what this is meaning to say is that when we are observing a piece of, so again, okay, let's, when we are observing a nebula, let's draw this as a nebula, not as uniform slab. We have atoms that decay at some point, and they all emit quanta of radiation. Okay, and each one has got h nu, you know, and so what we're observing here is the sum of all the Stokes eyes that come from this nebula. This makes a lot of sense, doesn't it? We're just looking at the superposition of all these quantas that come to the observer. It's quite intuitive. I mean, this is measuring the radiation flux. Let's remember this is connected to the pointing vector. Okay, so it's kind of obvious for Stokes eye, and we recover something very intuitive. What's not so intuitive is that the same additivity holds for Q, U, and V. Okay, so that's very handy. It means that the Stokes parameters are additive. So if they are additive, we can do this trick. We can decompose any set of Stokes parameters this way. Like you can imagine that these are a set of 4 equations. Okay, so we are writing it this way. I'm saying that I is I minus square root of Q squared plus U squared plus V squared plus Q squared plus U squared plus V squared. And I call this the polarized part. And this I call the unpolarized part. Okay, but this is just a formal way of rewriting the Stokes I. Stokes I then can have a polarized component, which would be the sum of the linear polarization, the other linear polarization, and the circular polarization. Okay. Now we write the similar sets of equations for the other Stokes parameters Q, U, and V, and we associate 0 to all the unpolarized parts. Okay, so this way we we describe the radiation intensity as completely unpolarized because Q, U, and V are 0, and in the polarized part, we see that Stokes I, which would be a Q squared plus U squared plus D squared and square root, is indeed it satisfies equation 43, that one. Okay, so we are happy that this term corresponds to the polarized signal, completely polarized. Okay, sorry. Good. So this is a trick. No, we can do this because the Stokes parameters are additive. Okay, so that's why I can handle them this way. But it is a hand trick because this way I can separate within any polarized signal. I can decompose into fully polarized signal and one fully unpolarized signal. So this is not easy to understand. Okay, so try to take some time to digest this. And this is very well explained, I think, I'm pretty sure is in the textbook. And it is crucial for astronomy, of course, because we learn from the polarization. The polarization of the wave is important to learn about the physical processes. Then polarization in astronomy is not always strictly required to achieve a specific result or finding. For instance, if you're interested in measuring the radial velocity of a planet, if you want to detect planet by measuring the radial Doppler shift, of course, of the star, then you're not interested in learning about the polarization so much, but if you want to detect a planet or something very tiny next to a very bright star, then you can use an interesting trick. If you want to do talking about planetary sciences, if you want to do like a radial velocity planet search, then no polarization is needed. Okay, so what if you want to actually image the planet? You have you have your planet, and you have a huge, amazingly bright star next to it. when you do this on in CCD astronomy, you cannot detect the planet because the glare of the star is just too intense. Yes, but there's an interesting trick here we can do. If this is reflected light, if this is shining in reflected light or scattered light, as we all call it, then this might be polarized. The light from the planet will be polarized. If we look at Jupiter, for instance, if we want to observe an exo-Jupiter in the light it reflects from its sun, then we can do the following trick. This is completely unpolarized because that's the star and it's not polarized. Normally, this is just completely stochastic. There's so many different quanta of radiation that they average out. There's no polarization. And so we observe this system in polarized light, in linear polarization, and we can cancel the stellar signal using the linear polarization. So now, as of 2021, at the current, like at the time now, today, this technique is used to image exo-asteroid belts. We can look at what's called debris disks. These debris disks are like exo-asteroid belts. You can think of them as asteroid belts. We can detect them using the reflected light next to a very bright star. Or you can also do the protoplanetary disks. Protoplanetary disks. Okay, so these are basically disks where planets are born. We can use this technique, the polarized light, to detect a very faint signal next to a very bright star. But with the advent of the 30-meter telescopes, like the giant Magellan telescope or the European extremely large telescopes, ELTs, we will be able to detect the reflected light from Jupiter's. So this is going to be a very important technique. Polarization is going to be a very important technique to detect planets, even though today it's not a very important technique. It will be eventually. There is another important reason why polarization is super important, and it's to do with the instrumentation. The electromagnetic signal is itself polarized. It's a vectorial signal, So if you want to design cameras, and coronagraphs, etc., you need to take into account the vectorial nature of the electric signal. And of course, in radio astronomy, polarization is very important for people who do AGNs, because synchrotron radiation, the acceleration of electrons in magnetic fields, is polarized. So this is just to convey to you the importance of polarization. Okay, so yes, just to summarize, we have that we define the polarization fraction as the relationship between the polarization of a signal relative to the total Stokes I. So we have this decomposition. This is the real signal on the left, and we artificially decompose it in two parts. And this part here on the right has got the good taste of fulfilling equation 43, which is valid for a fully monochromatic wave. So we call that the polarized part. And then we talk about the polarization fraction this way. This polarization fraction, when we have polarized signal in astronomy, we mean that this polarization fraction is between 2, 3, up to 5%. Okay, it's not incredibly polarized. It's a little bit polarized. Okay, it is a tiny fraction, 2 or 3%. So if it's difficult to detect something, because if you build a huge telescope to detect a very faint planet or a very faint star far away on the other side of the galaxy, this eye is going to be faint. We need a giant telescope to detect this faraway thing, you know, and detecting its polarization is even more difficult. It's about 100 times more difficult, you know. So that's why I mean that polarization will be the business of the future of the Giant Magellan Telescope, of the ELTs, and it's already the business of radio astronomers. Of course, it's always been for other reasons also. But this is just to say that maybe polarization might have seemed to you guys something boring in the past in terms of, because, you know, we don't tend to use it much in astronomy, really, but not that much. But it's going to become ever more important because it's now becoming within reach. It's possible to do accurate polarization measurement nowadays with the VLTs, and the polarization of exoplanets will be within reach of the Giant Magellan Telescope of the 30-meter dishes. Okay, so on Thursday, we'll be looking at this topic of wave propagation in a medium. So for that, I need you to fasten seatbelts here. I'm going to go fast, and it's not an easy topic, and it's not in the textbook. Okay, so this I took from Jackson, but we need it to understand the refractive index. And hopefully we'll then finish chapter 2 with this on Thursday. Okay, so if there are no questions, Nitya, yes?
Yes, Professor. I have a question. Like, I'm not able to understand a word that is secular resonance. So could you explain me what is the meaning of that? Like, I tried to search in books or internet, but I didn't get the satisfied answer. So yeah.
Where did you find it?
Actually, I found it in a paper, secular resonance.
But in what context?
It was about planetary stability of solar system.
Okay.
Yeah.
Okay, they probably mean, in that case, they do not mean something to do with the radiation spectrum. They probably only mean the orbital resonances. So when we have circular orbits, and you know that it is this idea that some orbits are stables with the 2-to-1 resonance, the 3-to-2 resonance, like that. Does that ring a bell to you?
Yeah, I understood like what is resonance, but I'm not getting what does that mean of secular resonance. Like,
the secular means over a few orbits.
okay.
It's like if you wait a few orbits, then there is a resonance. The secular is a time scale. So over maybe 10 to 100 orbits.
Okay.
So like, for instance, if you have it applies to many different systems, Nitya. Secular is an expression when you mean when you wait a little bit, basically. Okay. So when you have the three-body problem, you can have stable orbits. If you wait a few, and some orbits are unstable, you can, like just wait for 2 or 3 orbits, and then the third body will either collapse on the star or be ejected away. So that's what they mean.
Oh, okay. Okay.
But this is not to do with the polarization. It's more like, I think that what you're reading is probably to do with the gravitational dynamics.
Yes, yeah, I got suggestion like from one of my friends to ask this question to you, so that's why yeah.
Okay.
So they suggested me to ask to you, like you could explain like in a better way. So
well, that's what they mean probably. I mean, if you want, you can send me an email. just not to bore the others, but send me an email and I can try to point you to a better description of these resonances. Once I've got a better idea of what the context is of them.
Okay, thank you, Professor.
Okay, Nitya. So see you Thursday, everyone.
Wait, Professor, I have a question about coronagraphs.
Sí, coronografía.
How does that work? They just externally occult the source? Like they put a circular
Professor,
plate?
sorry, Andres, but I have a meeting now, and I was told to be early, so I have to go.
No problem. Just disconnect. I'll keep on talking to Andres, and that's all right.
Yes, Professor, I have to go to.
Okay,
as well.
Nitya, that's fine. Have a nice day.
Thank you, Professor. Yeah.
Ok, Andrés, parece que quedamos tuyo nomás.
Sí,
¿Cómo estáis?
bien, bien.
Mira, ¿y dónde te vino eso de esa duda de la cronografía? ¿De un paper que leíste?
No, le estaba pensando, es que siempre, o al menos cuando veí las imágenes del papers que usan Sphere,
Ujú.
me queda la duda si van y lo restan como externamente, ponen, no sé, algo en el instrumento que tape, o si lo hacen, no sé, como virtualmente, dentro ya luego de observar.
El típico, hay varias técnicas. Son todos como elementos ópticos del interior de la cámara. Y el más conocido es el que más se usa, el Lyochronograph. A ver. A ver si acá en Wikipedia tenemos un dibujo óptico bien bueno. No, mejor para atrás. A ver, images. Veamos esto. A ver si lo puedo zoomear. No sé si alcanzáis a ver, ni siquiera yo puedo ver.
Creo que si apretas control y después se suma y se...
Que estoy con, a ver, el control mouse, eso puede ser.
Pero entonces es parte del sistema, del diseño del sistema óptico el cronógrafo.
Sí, mira, está bueno este dibujo. Déjame sacar. Eso es el típico que hay, es el Lyochronography. Entonces... Ujú. ¿Cómo te está yendo con las postulaciones?
¿A becas? ¿O a qué?
No sé,
¿A
pues,
la U?
tu proyecto.
¿A la U? Bien, bien, sí. De hecho ya tengo hasta los pasajes listos.
Qué bueno, Andrés. Oye, mira, sinceramente yo sé que es importante para ti sacar este paper y para mí también, pero no, no está fácil la vida. No tengo, imagínate que yo no puedo ir a la oficina y trabajar full un día completo. Estoy acá, pernado en la casa, mi capacidad productiva ha bajado a 20-30% de lo que era antes de la pandemia. ¿Cachai?
No, sí, en verdad no. Con
Ah,
que me
sí.
digáis que ya no puedes, no es necesario ya, no sé, que más excusas. Y en realidad es totalmente entendible la situación y
Pero lo vamos a hacer.
sí. Igual ahora estaba participando de un workshop de Data Science en astronomía, así que me mantuve más o menos ocupado. Estaba en eso.
Mira, fíjate en esto. No sé si cachai un poco de geometría óptica.
Sí,
Ya, entonces este es un lente convergente y estos son rayos que vienen de infinito, ¿ya? Esta cuestión negra que hay acá representa la apertura del telescopio, básicamente. ¿Ok? Entonces, estos rayos que vienen de infinito convergen en el plano focal. ¿Ok? Del primer lente. Y claro, si tenía un lente que no viene directo, o sea, si tenía rayos que vienen de esta dirección. A ver si puedo anotar acá. Voy a ver si me funciona. Mira, no sé si te acordáis que, por ejemplo, si tenía un rayo que viene en esta dirección, sigue de largo y llega en este punto del plano focal, y si tú tienes rayos que vienen de esta otra dirección, llegan para acá y convergen en este punto de imagen. ¿Te suena eso?
Sí.
Ya. Entonces, si tú estás mirando una estrella y apuntas derecho a la estrella, los rayos de la estrella están representados por esto. En cambio, lo que viene del disco está un poco corrido de la estrella, entonces en el plano de imagen está corrido para acá. ¿Ok? Y le ponen aquí el coronógrafo. Es simplemente un pedazo de material que tapa en este punto focal. Luego pasan de largo y vuelven a construir la señal. Pero lo que hay acá, obviamente ya, todo lo que venía directo para acá ya está matado. Fue absorbido por este coronógrafo que está aquí. ¿Ok? Ahora, ese live stop no me queda muy claro cuál es la utilidad. Yo creo que ahí son como detalles que no cacho tanto. Creo que tiene que ver con estos anillos de difracción que se forman. Que cuando tú bloqueas, empezás a tener anillos de difracción y que para poder usarlo necesitas tener este line stop. Este es un diseño que finalmente te permite entonces tener la imagen inicial, pero sin esta cuestión gigante que tenía de acá. No está esto, pero tenía un costo adicional que son la difracción del... Este elemento óptico es un obstáculo y la luz se difracta en el obstáculo. Ese es el problema. ¿Okay? Entonces, esto de acá es para corregirlo y este es el padrón final que ves. ¿Okay? Hay otras técnicas en las cuales hacen interferencias destructivas en vez de colocar un tope así. Como hay un diseño óptico que es el loco, que es uno que se llama la coronografía Vortex. Déjame mostrarte. Vortex. Esto no tiene una página web. A ver, Vortex Chronograph. No. No. Pero a ver, maybe. Esto es. Esta cuestión, este elemento óptico que hacen, lo construyen así, con esta forma, para matar ciertos modos de la señal, usando, bueno, justamente interferencia destructiva. Igual es loco, pero
Sí,
lo ponen
bien
en el
raro.
mismo lugar, el mismo elemento, el lugar que el live stop, pero en vez de ser una cuestión que bloquea nomás, es una pieza así complicada. Eso es lo que llaman vortex coronography. Eso es lo que la llevan en este momento, para la coronografía. Oye, bueno, eso. Se me olvidó.